Hello, friends. It's Ben again, broadcasting from my beautiful back porch. I'm seeing that one of the trees is getting pretty barren of leaves and stuff. It's the weekend, but this is a video for the Calc 3 class. The video is about applications of multiple integrals. Specifically, it occurred to me with my previous video when I talked to y'all about joint probability distributions. I jumped in the middle instead of jumping in at the beginning. So what I want to do with this video is to take a look at probability, which I think is kind of a neat thing in the math end of stuff, but then the actual applications sort of part of probability ends up being much more important to, I started to say the natural sciences because that's what I tend to be more oriented towards, but really the sciences. If you are doing something with psychology, you are going to end up doing some kind of badass math with getting it to work. Psychologists end up doing some really good theoretical math just in getting the hard things that they work on to work. So, but this is a basic introduction to probability. We won't try to get anything very advanced or theoretical with it. All right. So, as per usual, let's find out whether the iPad will actually work today. So, screen mirroring. I let it display and I let it think about it for a second. Cross my fingers. And I'm going to do it. Great. Stop sharing. There will be a pause. Okay, let's try this again. Well, that's interesting. All right, get it to work. All right, so we are going to talk about probability stuff, and we are going to start a little bit with basics. Everybody should have this notion in the back of their heads of probability associated with rolling a die. You expect that the probability for rolling any particular number from 1 to 6 should be 1/6. Not hard, right? Now, if you're actually rolling and you roll 6 times, you will almost assuredly not get exactly that distribution. You know, it'll double up, you'll roll a 1 twice and no 5 or something like that. So that's the difference between theoretical distributions and empirical distributions. In the long term, we find that the empirical distribution for the die rolls, will end up being very, very close to the actual theoretical distribution. So this is an exercise in modeling a little bit. We have this notion of what the probabilities ought to be, and then we set up a model, a function that goes with them. In this case, the function would simply be, let's see, p of x equals 1/6. So every value that you plug in there, you have a probability of 1/6 for it, right? So then if you're a good scientist, you go and take that, that theoretical model that you have and go back and test it and gather actual empirical data and see whether it works out. If you're a mathematician, sometimes you just work with a model just to see what the model does, okay? So we're calculating here the probability that x is equal to 3. Well, if x is 3 and you plug into this function here, you will get 1/6. Boom, done, right? Now, if I ask you instead to calculate the probability that x is less than 5, this begins to move us towards a little bit more complicated idea because what we have here with the x less than 5 is an event. By an event, all I mean is a set of possible outcomes. So the set of possible outcomes for x less than 5 is going to be the x values from 1 to 4. And so we would actually go through here and just add up for x equals 1 to 4, the probability that big X is equal to that little x. And of course, that means we're taking 1/6 and adding it together 4 times. And then that turns out to be 4/6 or 2/3. Now, your natural reaction to that would be, there were 4 things there, it was out of 6, boom, I would have just done it like that. Then you're just being crazy and writing extra stuff you don't need to. No, mathematicians are by instinct lazy, but our laziness or my laziness in this particular case is because there's a point to it. When you have a distribution that's not uniform, then you'll have to do something different. So if instead of rolling 1 die, we were rolling 2 dice and adding it together, hopefully you'll realize from some exposure to this that rolling a 2 or rolling a 12 are much less likely than rolling a 7. That's because the only way to make a 2 is by rolling 2 1s. But to make a 7, you can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, you know, or the reverses of any of those. So that means that when we talk about calculating these probabilities, the probability for rolling a 2, there's only one way to do it out of 36 possible ways of putting your dice together, okay? And so if I wanted to say something about calculating the probability that x is greater than 9, I would still look here and say, well, x greater than 9 is this group here. It's a set of values, 10, 11, and 12. And so I would write the probability that x equals 10, the probability x equals 11, and the probability x equals, and I should have started farther over there, the probability x equals 12. And then I would go through and calculate each one of those. And I might have done this problem before. So I know offhand because of symmetry that the 12 is 1 out of 36. The 11, I know I can make it with a 5 and then a 6, or a 6 and then a 5. So that's going to be 2 ways to do it out of 36. And then the 10 will end up having 3 ways out of 36. So that means you end up with 6 out of 36 or 1/6. Now, if you want to use decimals for these, have a field day, you can use decimals. It's not a big deal. But I tend to use the fractions so that we can actually follow the logic out. All right. So with that first notion in mind of rolling a die, then that introduces this idea that we refer to as a uniform probability distribution function. We were using probability distribution function as an abbreviation long before the portable document format seized on the name. But I see sometimes now instead of talking about a PDF, you will see it referred to as a probability mass function. And while my instinct is to try to seize the name and keep control of it, the name there, probability mass function, man, that feels a lot like what you're doing in the physics applications that y'all have been looking at otherwise. So All right, so with this, in general, if it's uniform for our distribution here, okay, we need a function that, I thought I wrote this down somewhere, but I guess I did not. We need to have a function which is greater than or equal to 0 for all the possible x values. So if you looked at this graph outside the interval from a to b, you would see that you're getting zeros on it, okay? And then we need to have the total area under the graph turn out to be 1. And since we need to have it only be non-zero between a and b, then that means we have a rectangle that has a width of b minus a, so it has to have a height of 1 over b minus a. So if you're asked to write the PDF here, you would write p of x equals 1 over, what did we say here? A is 2 and b is 12. So 12 minus 2, so we would say 1/10. So if you're doing a uniform PDF from 2 to 12, the actual function you deal with is just the constant 1/10, okay? Now here, when we're asked, let's calculate the probability that x is less than 7, that's going to be a little bit different than what we've been seeing on these others. So let me try to write in here that we're going to have the 2 here, and we're going to have the 12 there, and that here we're going to have 1/10 or 0.1, however you prefer to do it. And when we say the probability x is less than 7, then we need to cut right here, say this is x equals 7, and we need to get the area that is to the left of that because it was less than. Let me redraw that because I'm unhappy with having a line that's not straight. So if we want to get this stuff that is to the left, we're just finding the area of a rectangle, right? The area of that rectangle, you would say, well, rectangle's length times width. So L times W, and the length, or maybe I'd say height instead of length, is going to be the 1/10. And then the width going from 2 to 7, you would just say 7 minus 2. So you would have 5, oh man, sorry, my letter got sloppy there. You would have 5/10 or 0.5, okay? And that's what you got of that, right? Now, on the other hand, if I said calculate the probability x is less than or equal to 7, there's no difference. I would go ahead and still say 1/10 times 5 and end up with the 0.5 or 1/2, however you want to write it there. I need you to realize this little weird trick here. When you have a distribution, there's 2 kinds of distributions. One kind is what we've got here of being a continuous distribution, whereas the kind before where we had the bars that were separated, that was what's referred to as a discrete distribution. For a discrete distribution, you just add up the bars. When you have a continuous distribution, you are instead looking at an area under a curve, okay? All right, so here's an example of a different distribution. It's referred to as the exponential PDF. So the exponential PDF has as the model here a function for all x's greater than or equal to 0 that involves a lambda. And the reason that this is kind of interesting is that your lambda, which for some reason my lambda here seems to have a mark across the top of it. Ah, well. So anyway, though, so having a parameter in there is something that you get to choose, and we have specific applications where we can see evidence that an exponential distribution is what we need to work with, but we need different values, okay? So here I'm just giving you that the lambda is equal to 2. In an actual honest to goodness application-y problem, you would know that you're needing to work with an exponential distribution, and you would have more evidence tied together where you would know how to do these, okay? So you would have some reason behind the lambda as opposed to just being given the lambda, all right? So we are going to calculate that the probability, we're going to calculate the probability x is less than 3. So 3, pretend that it's this number here, and we need to get this area to the left of it. So that means for doing this, that we'll just say this is equal to the integral across that portion of the support. Support is a word for this here, the part of the function that's not 0. See the 0 part here. So the part of the function that's not just uniformly 0 is referred to as the support of the function. We want to integrate across the portion of the support that is in our event. Our event is x is less than 3, and our support is x is greater than or equal to 0. So we will integrate from 0 to 3 because that's in both the event and the support. And what we will integrate is just the lambda e to the minus lambda x dx, okay? So in doing that, you're gonna do a u substitution, and the u is gonna be the minus lambda x, and that means that you will scoop up the lambda inside of the du, and you'll end up, for an answer of this, getting minus e to the minus lambda x, evaluate 0 to 3. And so you plug in the 3 at minus e. Oh, I'm a silly head. I will have to fix this in a second. To minus 3 lambda, and then minus a negative e to the, when you multiply lambda by 0, you get just 0. So we'll have 1 minus e to the minus 3 lambda. Now, if you're following along here and you say, hey, Ben, why did you not put in the 2? Psh, good question. Why didn't I put in the 2? So let's just go back and put the 2 back in here. Notice, though, that whole calculation, it didn't really hurt my hands with writing too much to have the lambda there instead of having the 2 there, right? So that means that you could actually do theoretical calculations just as easily as you could do calculations for particular values, right? And then if you want to get a decimal for that, you can get a decimal for it. I don't have a calculator at hand right now, so I'm going to just leave it at that, okay? So this represents the probability that our value of x will end up being to, what did I say? To the left of 3, and that is 1 minus e to the minus 6. Gosh, e to the 6th is going to be like, I don't know, maybe 2, 3 or 4 1,000ths, I think. That's just an estimate off the top of my head. So this is like going to be something like 0.99 or more than that. So the vast majority of this distribution is going to be to the left of the 3. So, all right. So another distribution that you'll spend a lot of time with is what we refer to as the Gaussian distribution or the normal distribution. So the normal distribution has this kind of a bell shape to it. It's given by a function that has e to the minus x squared in it, but then it gets more complicated from there. I believe that it's e to the minus quantity x minus mu closed quantity squared divided by 2, yeah, sorry, 2, I think divided by 2 sigma squared, and then there's supposed to be like a 1 over root pi out front or something like that to make it all work out nicely. It is in general something that you just can't do the integral of off the top of your head. You know, it's just not nice. But we do have this observation. This is referred to as the empirical rule. For a normal distribution, approximately 68% of the area is between plus and minus 1 standard deviation. Standard deviation is, we'll refer to as sigma. It's just a unit of measure about these distributions. Not going to try to get into that very much here. We find that between plus and minus 2 standard deviations, we get 95% of the curve. And between plus and minus 3 standard deviations, we get 99.7% of the curve. So if I were to ask you here that for the mu being 0 and the sigma being 1, to get the probability that x is between 0 and 2, then on our picture here, you would see that that means you're to the right of center, and that you're not going to go out past that 2 sigma mark. And so consequently, you can see that you must be getting half of that 95%. And so that would be about 0.475, okay? Now, if you need a more exact number than that, you turn to numerical routines. Anybody who's had an AP Stat course knows that you just look this up in a table. Okay, let me rephrase. Anybody who is like 5 million years old, like me, knows that you look it up in a table. Everybody else just goes to their calculator and feeds in the lower and upper limits and what the mu and sigma are, and it just gets you a number. And that's because the integration is just too hard to do. So we always do it with numerical routines. All right, so this is all leading up to us talking about this notion of a joint probability distribution. So you have 2 random variables, capital X and capital Y. We use the capitals to denote a theoretical model that we're working with, and then we use the lowercase x and the lowercase y to represent actual observations. So the function that we think about with this is going to be a function of 2 variables. The requirements for that function are that it be greater than or equal to 0 for all values. And then if you, I probably should use an S instead of an R here, but if you integrate across all the possible values, you should get a total of 1. That's all the rules that you have for this. So that function could be practically anything, right? But then if you want to get the probability of some event, the event here is going to be a set, and the set is going to be described by some inequalities or something or another with the x's and y's. Anyway, you integrate across the event in order to get the probability of the event. I think that's kind of a neat, compact way of writing this stuff down. But anyways, so then the other big concept here is the notion of independent variables. Variables are independent provided that the function, the probability distribution, joint probability distribution function is going to be the product of a PDF for the x's and a PDF for the y's. And that function needs to not depend on either the probability for the x's, the g of x, because it needs to not depend on the y's, needs to be the same no matter what the what it is that we're talking about. So here in our picture, the cross-sectional area needs to be the same no matter what X value you choose. And if you talk about the cross-sectional area on the Y's, that needs to be the same no matter what Y value you choose. If you recall, when we were doing integration, I've given you all the tip occasionally that you can separate the double integral out into two integrals, but that requires, first of all, that you can factor the function into two pieces, and then that you have a rectangular region of integration. So our idea of the independent variables requires both that it's factorable and that you have a rectangular support region. Okay. All right. So quick example here, we're going to have a uniform distribution or a joint, oh man, I hate the phrasing here, a joint uniform distribution for the X's and the Y's. So the support on this, we're going to have the X's go from 0 to 10 and the Y's go from 0 to 20. So consequently, if I drew a picture of it real quick, then I know that my interval that I've got for the X's needs to be much more narrow than the interval I've got for the Y's. And so it would look something like that, all right? So that's X equals 10, and this is Y equals 20. All right, so now we need to find a C value so that our distribution here, f of xy equals c, that should have been a lowercase f, sorry. That is a valid joint probability distribution function. Now, of course, you're going to integrate it across this region here, and the region has an area of 200. So that's going to tell you, oops, forgot to change tools, double integral across the region of the CDA is going to be 200C. And since that needs to be equal to 1, then your C is going to be 1 over 200. Okay? So then we will just write out here f of x comma y equals 1 over 200. If you prefer to write it as 0.005, go right ahead. All right? So now with this portion here, we need to say calculate the probability that x is less than y. So what's going to be helpful for us on that is to actually draw the picture of x equals y. So going up here to my graph, I'm going to draw just a straight line across where x is equal to y. I probably should have started it farther down here. And I need x less than y, and that's going to mean that I need this portion here. Okay, so if I want to do my double integral across my event of this 1 over 200 dA, then I'm going to have to say integral 1 over 200 d something, okay? Now, if you're looking at that region there, you will have spotted that it is vertically simple. So we probably want to do the integration that way. So I would integrate dy and then dx, and the y is going up, hit the x first, and then they exit at 20. And then for the x values, it's going to go all the way across from 0 to 10. Okay, and that's an integral that's actually pretty easy to do here. You could, in fact, do it totally geometrically by saying I factor out the 1 over 200, and then I take the area of that trapezoid there, and then you might look at the trapezoid and say, Well, that is going to be, how do trapezoids go again? It's the height times base 1 plus base 2 over 2. The height there, I guess it's sideways height, but that height is 10. And base 1 and base 2 are 10 and 20. So that means that you end up with 150 over 200, which is 0.75, or if you prefer the fraction, 3/4. Okay, either way. So that's the sort of thing that you have to do on these. You have to spot what the region is by drawing pictures based on whatever is used to describe the event, and then integrate over the region that's involved. So, yay. Then this other bit here is that we should talk about the expected value or the average for a function. So if we're talking about a single variable, all we mean by the average is that you take the function, multiply it by the probability distribution, and then integrate over your support. You've actually done this before, all right? If you collected a bunch of data from a lab science class or something, you always end up averaging it. When you average it, what you've done is to assume that the probability of all 20 pieces of data, whatever they were, is 1 in 20. And then you added up the score times 1/20th, the score times 1/20th. Now, you were too smart to actually do it that way. You just added and then divided by 20 at the end instead of dividing by 20 times. But that's essentially what's going on there, right? So for what we're going to do here, we're going to calculate this. Oops, forgot to change tools. We're going to calculate this e of x, the expected value of x. So we're going to integrate, and we're doing an exponential distribution. So that means we're going to integrate 0 to infinity, because that's the support here. And we said that the lambda is going to be 2. So we'll have 2. Oh, I should not have written that yet before I put that. Come on. There we go. Before I put that in, I need to put x and then the lambda, 2e to the minus 2x dx. Okay. And of course, if you're actually doing that integration, you're probably saying, oh no, I didn't want to do that, because when I do that, then I have to do an integration by parts and all kinds of yucky stuff. So I, on the other hand, am saying, oh no, I don't want to switch windows. I'm going to just do this with Symbolab, okay? But I'm not going to switch windows and show you, because if I do, I might have to reboot my damned iPad again. So, but I'm just going to integrate from 0 to infinity the 2x e to the minus 2x. And the value that I got out here was 1/2, okay, or 0.5, however you want to write it. Now, the thing that I do down here, or I ask you down here, is to get the expected value of x squared, because you don't have to just do the expected value of x. You could have x squared or sine x or anything, right? And we're going to see that come up with the joint PDFs here in just a second. But when I come back and ask it to do this for the x squared, I get, that's pretty weird. So equals integral 0 to infinity x squared times 2 e to the minus 2x dx. The expected value I get for x squared is also 1/2. That's kind of weird. I wonder what happens for x cubed and stuff. Yeah, but I'm going to put the note here, used Symbolab. Okay. All right. So let me jump back across. Oh man, my Windows on my computer is not showing me what I want. So I am screen sharing. Wow. Okay. I'm having a little bit of weirdness on the computer here. I certainly hope that you can still see the screen that I'm sharing. I'm going to hit stop share and then redo it. God, I hope it works. Yay, it worked. Okay. All right. So we use Symbolab for that there. All right. So then we're going to do an expected value for multiple variables. And it's really going to be just the same thing. So in this case here, I went ahead and just designed us a function that I knew was going to actually work out. So this one does turn out to be a valid joint PDF. You will notice a lot of your problems will say, hey, let's just stick a random, some random parameter in there and make you figure out what it has to be. So for that, if I'd wanted to do that, I might have put a C here at the beginning of this and ask you to figure out what it had to be. And then you would integrate just this from 0 to infinity for both the X's and the Y's. Okay. So in fact, I probably ought to have X greater than or equal to 0, Y greater than or equal to 0. Okay. All right. So then for finding the E of X here, that's just going to be that we'll do the double integral across the support of X times our f of xy dA. Okay. So for the purpose of doing this, you would set it there and have X times, and then it's 0.1 e to the negative 0.5x minus 0.2y d something d something. Now, because it's the whole plane, it's going to be a rectangle, and it doesn't really matter if you do dx dy or if you do dy dx. Both of them are going to go 0 to infinity. Okay. If you have a region that is not a rectangle, then you have to actually pay attention to it. Okay. But when I do that integration there, I am, just like before, going to have to do an integration by parts. And that's not always going to be super easy to do. So the thing I'm going to do is to, again, cheat and get Symbolab to do my actual work for me. And I am going to just put a 0.1 e to the minus 0.5 x minus 0.2 y, and I multiply it by an x, right? Yeah. And then I did dx dy, and I will just tell it to evaluate for me. Again, if you didn't have the luxury of Symbolab, you would have to do integration by parts, but that should be totally within your wheelhouse. So doing that work, Symbolab comes up with an answer of 2, right? Then the second piece on this says now we're going to have, and I could totally ask it to be doing the expected value of y as well, but I purposely chose here to have just another function. And so the function here is going to be x plus y, f of xy dA. So then I'll do the integral 0 to infinity again. on both of those. Instead of an x, I'll have an x plus y. Okay, and I am going to come in here and type x plus y where I had an x before. I'm just going to let the computer evaluate for me. I believe it'll come out to be 7. The computer's being super slow about it. And yes, and it did come out to be 7. By the way, here's something that is convenient to know. The expected value of x plus y, expected value is a linear operator, and linear operators you can go ahead and distribute out like that. Since you know the expected value of x is 2, and you know the expected value of x plus y is 7, then you can figure out the expected value of y turns out to be 5. Kind of neat, maybe not all that earth-shaking though. So, all right. But that's the essentials of probability theory. I haven't gone into anything really theoretical. It's just the definition and then having to do all this stuff with an integral in it. So if you were taking an AP Stat course or our elementary stat course, you would never do integration because that is an algebra-based class, not a calculus-based class. So I guess that's where to leave things on this. All right. I will see you all on Monday. Have a good rest of your weekend.